Hi everybody, it's been a few weeks now since I last did a video. The reason for the delay has mainly been due to family commitments and other work I had to complete. But having got that out of the way now, I'm managing to get back to electronics. So I thought today, as a start off, we'll have a look at designing and building a stair-step generator, and I'll add into that one or two extra features and also use some components which you could use for other projects at a later date. So let's get started with this project today. At the heart of our project today, we're going to use a Johnson counter. It's a little bit different to normal counters in as much as that the clock pulse coming in on the clock input there on pin 14 in this case gives us a sequential pulse coming out on Q0 through to Q9. So effectively what you get is you get the divide by 10 of the frequency, but rather than get a equal mark space ratio of the signal coming out, on the rising edge of the first clock pulse you get a pulse coming out on Q0, and then the rising edge of the second clock pulse you'll get a pulse coming out on Q1. And what you'll find here is that on Q0 through to Q9 you'll get a sequential pulse coming out from this Johnson counter, which is ideal for our project today. Now, each of these pulses will have an amplitude here of 5 volts peak to peak, because we're using a 5 volt supply to drive this IC. Now, this particular IC is available in two types. You can get the TTL version of this IC, which is usually supplied with a 5 volt supply. It can operate, I think, from 2 to 6 volts. But there's also a CMOS version which can operate all the way up to around 15 or 16 volts. But for our project today we're going to stick to the lower voltage TTL version of this particular IC. Now, in addition to the sequential pulse outputs we've got coming through Q0 to Q9, we also have a carry output coming on pin 12 of this IC, and that'll give us a divide by 10 output, but this time it'll have an equal 50-50 mark space ratio. And we'll simply use that again in our project today to give us a sync signal coming out, which we can use either to lock the trigger on an oscilloscope, or you can simply use it to give you a frequency reference coming out where you need a equal mark space ratio. Here you see the circuit I've put together to give us our stair-step waveform coming out from the 4017 Johnson counter, which is fed with a pulse input on its clock input. And basically what we're doing is we're taking the pulse outputs from Q0 through to Q8, feeding them through some DC blocking diodes there. Remember that when we've got no output pulse on any of the pins here, the logic level is 0, and therefore the diode will be switched off. So the diodes only conduct when it sees an input pulse, a positive input pulse on its anode. It then feeds that positive pulse to a resistor divider network, which has been specifically chosen to divide the pulse amplitude down to give us the steps of the stair-step waveform coming out. So the first pulse coming out from this counter is fed to ideally a 7.68K in series with a 1.2K, and that is generating a pulse amplitude there, Q0, of around 0.6 of a volt. When the second pulse comes along, all the other outputs are 0, so only that diode there is turned on. It feeds the second pulse then to that 3.24K resistor and the 1.2, and that gives us an amplitude, voltage amplitude of that pulse of twice the previous one, so we're getting 1.2 volts pulse coming out there. So that's giving us the Q1 step. And you'll see from this sequence that as each of the outputs go high, it turns on one of the diodes and feeds it through a potential divider that gives us the correct amplitude to produce the steps of that stair-step waveform. Now what you'll find is that when you get to Q4, which is the top of our waveform there, we now want to step down on Q5. So you'll notice here that the output from Q5 is fed to the same resistor divider network as we had for Q3. So that step is equal. And you'll see that we've done exactly the same for the other outputs from Q6 to Q8, where we're using the same resistor divider network we had on the upward steps to produce the downward steps. Now, as we only need to use Q8 from Q8 to Q0 there to give us our stair-step waveform, we will ground the Q9 output down to chassis to prevent any noise affecting the output of the signal. Now, what I've found is that the resistors here obviously are quite critical to get the equal steps in that waveform. That'll give us around 3 volt peak to peak waveform, stair-step waveform coming out. And what I've also decided to do is make that 1.2k resistor have a fixed and a variable, a little trim pot there, so we can trim the output signal to make sure that the shape of that stair-step waveform is equal steps. Here I now have the oscilloscope connected to the Johnson counter, looking at the input clock signal there, which is in yellow. That's our 100 kilohertz square wave coming in at an equal mark space ratio. And then I'm just looking at Q0, Q1 and Q2 just to illustrate the pulse outputs coming from the outputs of this Johnson counter. And you can see quite clearly that on the leading edge of the clock pulses it triggers one of the outputs. So on the first leading edge of the clock pulse there, it triggers Q0, goes high and stays high for the duration of the first cycle, and then it goes low and remains low at the end of that. And then on the leading edge of the next clock pulse there, you can see that Q1 goes high and stays high for a cycle of the clock pulse. And the same thing happens for Q2 there. That goes high on the third clock pulse on the leading edge there and stays high for the duration of that clock cycle, and then goes low again. And you'll see that repeated all the way through the outputs of this Johnson counter. I will just connect the oscilloscope, the last trace there, onto the carry output just to illustrate that we do have a equal mark space ratio coming out on pin 12 of this IC, which I said we will use as a sync output. Right, well, here now you can see on the bottom trace there we're looking at the carry output on pin 12 of the IC, and you can see quite clearly there that we've got a nice square wave pulse coming out with an equal mark space ratio, and that is divide by 10 from the clock frequency going in. As is the other pulses, they're also divide by 10, but obviously the mark space ratio is a much shorter pulse on the normal output pins. Here we now see the clock pulses, and comparing that now to the stair-step waveform coming out from the resistor divider network, which is coupled to the output of the Johnson counter. And you can clearly see there that each one of those steps is equal to the width of one cycle of the clock frequency going in. Now that particular stair-step signal here is round about 3 volts peak to peak. What we're going to do in our project today is put a buffer stage on that and an amplifier to give us a 5 volt peak to peak signal coming out. I'll just quickly take you through the process I went through to calculate the values of the resistor in the divider chain to give us our stair-step. I'm illustrating here the output of Q0 from the Johnson counter, and the Johnson counter is fed from a 5 volt supply, and therefore the pulse coming out at Q0 would be 5 volts peak to peak. But we've got a DC blocking diode there, and you're going to get a voltage drop across that of around about 0.6 of a volt. So by the time the pulse arrives here, the pulse amplitude is going to be around 4.4 volts peak to peak. Now if you then consider that on the output here we wanted to generate a stair-step waveform which will be 3 volts peak to peak, so we're looking there for 3 volts peak to peak. That means that each step of that waveform will be 0.6 of a volt. So what we're looking for here is that the first step of the waveform there should have an amplitude of 0.6 of a volt. And what I did initially was choose a fixed resistor for the bottom end of the chain, and this will not vary once we've set it. So I chose initially 1.2K. It's a standard value resistor. As you see in the diagram later, we'll replace that with a fixed and a variable trimmer to give some adjustment, but effectively we want a 1.2K. And to generate 0.6 volts on the output, the current flowing through that 1.2K will be equal to I equals to the voltage divided by the resistance. In our case, it's equal to 0.6 divided by 1.2 K, that's thousands, and that will give us, in milliamps, it'll give us 0.5 milliamp of current flowing through the 1.2K resistor, and that'll give us our 0.6 of a volt. That means that the voltage drop across that resistor R there is going to be the difference between 0.6 of a volt and 4.4 volts. So across the resistor there, we need to drop 3.8 volts. And I simply calculated the value of that resistor. R is equal to the voltage divided by the current. So the voltage is 3.8 volts. And the current we know going through this chain is half a milliamp, so it's 0.5 milliamps, so the result will be in k ohms, and that will give us 7.6 k ohms. And that's how I calculated the resistor there in this divider chain. Now the nearest value I can get to that is 7.64k, and that's what I chose. But you can also use a standard value of 7.5k, and I found that works quite well. I then simply went through this same process for the other resistors, and this time calculating it on a different voltage output across the 1.2k. So on Q1, the amplitude of the next pulse will be double 0.6, so that'll be 1.2 volts. So I calculated 1.2 volts across the 1.2k. And that gave us the current, and then I calculated then the voltage drop across there and worked out the resistance of that because we know the current flowing through it. So that's how I did my calculations for those resistors and gave me those strange values. But as I said, you can actually purchase those values and get them in 0.1 tolerance. Here we see the block diagram for our project today. I'll just quickly run through it for you. Again, I say the heart of it is going to be the Johnson counter that's driving a diode and resistor network, which will give us the stair-step waveform coming out. And it's that waveform that we can then adjust the symmetry of with a little adjustable preset there to trim it at the setup stage. And the output from that is fed through a buffer and then through a op amp, which is adjustable, little preset there, so we can set the output to deliver exactly 5 volts peak to peak. Now it's worth mentioning that the power supply for this project is going to be given from either a 15 or 18 volt DC supply, and for that I'm going to use a little mains adapter DC supply module here. These are picked up quite cheaply these days on eBay, and that will give us the DC supply voltage going into the 12 volt regulator, which in itself feeds the 5 volt regulator, and the 5 volt feeds the logic IC and the oscillator circuits for this project. The 12 volt supply is feeding a rail splitter there. We've got a Texas Instrument TL2426, nice little IC there, again relatively cheap, for it cost around about £2. And that will split the 12 volt supply rail to an accurate plus or minus 6 volts, which we're using for the operational amplifier stage on the output, to allow us to have a output waveform which is symmetrical around the 0 volt mark. Now the input to the Johnson counter is supplied with a clock pulse either from a fixed reference oscillator, which is switchable, or from a variable oscillator. Now the switched reference oscillator, I'm using a little module, a 1 megahertz module, to derive the frequency, and then I'm dividing that down with a 74HC390 in 2 stages of divide by 10. So the first divide by 10 stage will give us 100 kilohertz output, and the second will give us 10 kilohertz. Now, depending on which one you want to use, I'll either simply use a switch here to switch between the two, or on the little project board today I'll put a little link in so we can link either the 100 kilohertz or the 10 kilohertz signal, and then we put another link in here to supply it, or a switch to supply it to the clock input to the Johnson counter. The other alternative for the frequency input is to switch this to the link to the top there, and that then connects to a little variable oscillator circuit, and for that I'm using the Linear Technology LTC 1799 IC. A nice little chip. It comes in a very small SOT23 5-pin package, so a little bit more difficult to solder onto the board, but I'll show you that later. But the nice thing with it is that with one variable resistor you can adjust the frequency, and it is very stable. And the other nice feature of this IC is it has a pin connection on the IC itself, which allows you to then select a divide by 1, divide by 10 or divide by 100 for the frequency output, simply by switching that pin to either ground, no connection, or supply plus 5 volts to give us those divider options. So there we are. There we have the two frequency inputs to the Johnson counter, and either we use a little link on the module, which I'll show you today, or you can simply connect it to switches on a front panel of a little project box if you decide to do that. Now, the other option with the project is we have the carry pin from the Johnson counter, which I'm going to then just feed out to an output socket, and that will give us a square wave output with a symmetrical 50-50 max-base ratio of divide by 10 of the input frequency, and we can either use that, as I say, as a trigger for a oscilloscope, or as a accurate reference source. I'll cover the circuit diagram in two parts. First of all, we'll have a look at the power supply arrangement and the oscillators and the divider circuit for the oscillator. So let's have a quick look at that. We covered obviously most of this on the block diagram, but here we can see all the component values mapped on the circuit now. The input is decoupled by a 1000 microfarad capacitor, either that or a 2200, but 1000 will suffice. We have the usual 0.1 or 100 nanofarad capacitors across the input and outputs of the voltage regulator ICs there, using the LM38112 and the LM3805. There you can see we've got the 12 and the 5 volt supply. The 12 volt supply is also fed to a rail splitter IC, the TL2426, as I mentioned earlier, and that's going to give us a virtual ground output for the operational amplifier and buffer stage at the output, and effectively that'll give us a plus or minus 6 volts DC. Here we can see the oscillator circuits feeding the Johnson counter. The first one here, the LTC 1799, is the variable oscillator I'm using. The supply there is decoupled by a 0.1 capacitor. The output coming out on pin 5 of that IC, and you can set the frequency by a resistor from the set pin, that's pin 3, up to the plus 5 volt supply. And what I've done there is I've got a 100k limiter resistor there in series with a 1 meg preset or variable resistor. The other feature of this IC is the fact that we can divide by 1, 10 and 100 by simply switching pin 4 of that IC either to ground, leave open circuit, or to plus 5 volt supply. Now, the output of the oscillator pin 5 is connected to the Johnson counter clock input either via a switch or a link. So I've just shown it there at the moment as 2 pins, so we can put a link across that, and that's what you'll see when I show you the circuit module that we built today. So that's the adjustable oscillator circuit. The fixed oscillator circuit for this project is using a 1 megahertz crystal oscillator module, little module, 4-pin module. and that gives an output on pin 3 of 1 megahertz, and you supply that with 5 volts DC, and again we've decoupled that with a 0.1 capacitor down to ground. The output of that is fed to a 74HC390, which is a dual divide by 10 IC, and the configuration here, as you can see, we've wired it up as divide by 10 followed by another divide by 10 by adding the links as shown. So I've just indicated the pin connection numbers there, and the output on pin 3 is at 100 kilohertz, that's divide by 10, and the output on pin 13 is the divide by 100, and that is giving us 10 kilohertz out. So again, we can switch between the two either with a switch or with a shorting link, so we can put a link across the two to give us whichever we want. On the module again, I'll show that as links for the moment, and then again we can link that via another link there to the input of the Johnson counter, the clock input, to supply that with the clock pulses. So there we have the options with the oscillator circuit and the power supply arrangement for this project. So let's now have a look in more detail at the Johnson counter circuit and the output stage. Right, well, here we see the remainder of the circuit today. The output from the Johnson counter is feeding this resistor divider network through some DC blocking diodes here. Now I've already explained this earlier, so I won't go through that again, but suffice to say we'll be looking for a 3 volt peak to peak stair-step waveform at that point there, the output of the divider network, and we'll set that by trimming that 1K preset resistor there. We've replaced the fixed resistor we had earlier with a 1K in series with a 1K trimmer, so that'll give us some adjustment to set that 3 volts peak to peak, and also give us some symmetry in the equal steps of that waveform. Now the output of that is fed through a 10 microfarad capacitor to a buffer stage there. We're using 1/2 of the NE5532 as a buffer, and the output from the buffer is then fed to the other half of the NE5532, which acts as an amplifier, and the gain of which is set by the 10K resistor there. Now you'll notice here I've got a 1K in series with that 10K preset. You may find, depending on component tolerances, that you may not be able to trim that gain down such that you get 5 volts peak to peak out. You may find it hovers around 6 volts peak to peak, in which case if you have that problem, simply replace that 1K resistor with a shorting link, and then you should be able to adjust the 10K preset sufficiently to give you exactly 5 volt peak to peak out. Now the operational amplifier, the output stage there, is fed with plus and minus 6 volt supply, and that's derived from a rail splitter IC there, the TLE2426, and that's taking the 12 volt input and giving us a virtual ground there at its output. So that is a virtual ground, and it means that the supply then going to the operational amplifier is effectively plus and minus 6 volts. Now the other additional feature I thought I'd add to this project today is the ability to provide not only the stair-step waveform, but also to give us some steps, either 1, 2, 3 or 4 steps, and we're doing that with a pulse selector switch I've added here, and simply in the 0 position, which is at the moment, the reset pin of the IC is connected to ground, so the Johnson counter is free running, so it just cycles through and gives us the stair-step waveform. If you then flick the switch through positions 1 to 4, you'll notice now that we're connecting the reset pin of the IC to one of the outputs from the Johnson counter and terminating the cycle early, and that's what's giving us either 1, 2, 3 or 4 steps in place of the stair-step waveform. And finally here on the output of pin 12, we're taking what I've called the sync output, which we can use an external trigger signal, and that gives us the divide by 10 signal, which has exactly got an equal mark space ratio of 50/50. So there we have it. That's the output stage of our circuit today. So the next thing we'll do is we'll build this on a printed circuit board and test and set it up. We'll just have a quick look at the components for the project today. As you can see, I've produced a small printed circuit board for this project, which I'll be making available with the artwork as a download. And just quickly going round the components, we've got the two voltage regulator ICs there, the 12 volt and 5 volt regulator, the IC sockets for the project, two 16 pin and one 8 pin, the electrolytic capacitors 2200, 470 microfarad, and there's a couple of 10 microfarad capacitors there. The rotary switch here is the 6-way 2-pole rotary switch, the printed circuit version of that. And there you can see we've got a group of 100 nanofarad or 0.1 microfarad capacitors, which are used as decoupling throughout the circuit. The resistors here for the project, this little group here of resistors, slightly higher tolerance than the others. These are a 0.1% tolerance, and I'll be using them as the divider chain that we're using on the output of the Johnson counter to improve the accuracy of the stair-step output. Here you can see I've got some SIL connectors, and I'll be using these as the shorting pin connectors to set different options on the generator, together with these little shorting plugs we've got here. I have a few printed circuit pins I'll be using across the board, using these mainly for the outputs and the power input connections to the board for the moment. There you can see I've got some small switching diodes, the 1N4148s. They're using as the isolation diodes from the Johnson counter IC. And this little looks like a transistor. It's in a TO92 package. That is in fact the rail splitter, which is giving us the virtual ground for the op-amp output stage. And that particular one there is the Texas Instrument TLE 2426 type. Now this little chip here is the Oscillator Ic from Linear Technology. It's an LTC1799. It's in a very small TSOT23 5-pin package, so you need to be fairly careful when you're soldering this onto the board, but I have made pads available on the board to solder that on, but you'll need a very fine tip soldering iron to do that. Here we have the preset resistors for the project. We've got a 1 meg, a 10k and a 1k preset, and these are the other ICs for the project. We have the 74HC390 chip. We have there the Johnson counter IC, which is the 74HC4017 IC, and there you can see we've got the little dual op amp, and that one we're using is the NE5532. This module here is the 1 MHz crystal oscillator module, 5 volt version, and that just solders straight onto the board. So there we are. There we have the all the components for the project today. What I'll do next is I'll mount them on the board. The first thing we're going to do here is mount the little oscillator IC, which is a surface mount component, onto the PCB side of the board. And here you can see the position for that chip. It's a TSOT23 5-pin package, so it really can only go on one way, but I have indicated with a little dot there, pin 1 of that IC. And the first thing we're going to do is tin that area there, tin the pads, and then clean it with some solder braid before putting some flux on and then soldering the little IC on. So let's first of all just tin the pads. Of course, here you need a clean and fine tipped iron to do this. And now I'm just going to clean off the excess with some solder braid. Next I'm going to just put some flux on there with a little flux pen just on the connections there. and we'll now mount the IC on there and solder it on the board. Here's a close-up of the little oscillator IC now mounted on the board, soldered in place. And just a little tip here, once you've positioned the little IC on the board for soldering, I found it the easiest way is to solder that pin there, the bottom right as you can see, first, because you've got more spacing between the pins there, so it's easier to solder. It just locks then the IC in place and then allows you at your leisure then to go around and just tack the other pins with solder. So there we are, there we have the oscillator IC now on the board. So I'm going to mount all the other components now. Here you see now the board with all the components mounted. I haven't installed the ICs yet, although the surface mount IC is soldered onto the PCB and the oscillator module is also inserted. Also take note of the orientation of the 12 volt and the 5 volt regulator ICs, and also the rail splitter, which is for the virtual earth. Note the orientation of that when you're positioning it onto the board. We'll have a closer look at that in a moment. Now before we insert the ICs, I want to test the board for the correct 12 volt and 5 volt supply. You'll find those indicated on the printed circuit side of the board. And I've also left out for the moment two links, a link there which is J11 on the circuit diagram, and another link there which is J8 on the circuit diagram. I've left them disconnected for the moment until we check for the correct 12 and 5 volt supply on the board, just so we don't do any damage if we have any issues with regard to the voltage supplies. Here we can see now a close-up of the TLE2426 IC, which is the supply rail splitter or virtual ground IC, and it's important that you have the correct orientation of that when you solder it onto the board. You'll notice here I've got the flat side facing in that direction, and you'll see that the center pin is coming out toward it. So just be careful when you're soldering this particular IC onto the board. Just a quick indication on how to check the 12 and 5 volt supply once you've got the board in this position. I've just coupled here positive and negative. I've got 15 volts going in there on the input, and I've connected the ground pin of my test meter to that earth connection there. And what we'll do first of all is the red link wire here on the right hand side, we can check there the 12 volt supply, and on this IC socket here on pin 16, which is there, we can check the 5 volt supply, and I've just tested both of those and they indicate correct on the meter. So what I'll do now is I'll put the two links in and install the ICs, and then we can check the module fully. The next thing we're going to do is set up the units, and in order to do that I need to put some shorting links in to set the frequency going into the clock input of the Johnson counter to 10 kilohertz. And what we're going to do initially is use the fixed crystal oscillator and the divider IC there I'm pointing out. Just above that you'll see there's 3 pins where we can set the frequency. The center pin is the common pin. The one to the left sets it to 10 kilohertz, and the one to the right sets it to 100 kilohertz. So what we're going to do is put a shorting link on the left 2 pins there, and then if you look to the right there you'll see there's 2 pins there, and above it there's 2 more pins. We're going to put a shorting link across the bottom 2 pins, which then send the frequency from the fixed oscillator to the clock input of the Johnson IC. So let me just put those links in. There you can now see I have the 2 links in place. The blue link setting the frequency to 10 kilohertz, and the yellow link plug is setting the fixed oscillator output and it's connecting it to the Johnson counter IC. The next thing we're going to do now is connect the oscilloscope to the output of the divider network, resistor network, and we're looking for around 3 volts peak to peak there, and we'll also now adjust the little preset resistor in that network to ensure it's 3 volts, and also we have some symmetry in the steps of the waveform. Right, well, now we have the oscilloscope connected to the output of the resistor divider network there, and the earth lead of the oscilloscope is going to the ground pin on the left hand side of those sync connections there. The other important thing at this stage is to have the rotary switch turned fully anti-clockwise. So now let's supply some power to the unit. I've got 15 volts leads going into the power input there, so let me switch that on and monitor the output waveform. I have now powered the unit, and the oscilloscope is looking at the moment at the output from the resistor divider network there. So we're looking for around 3 volts peak to peak. At the moment you can see the waveform on the oscilloscope is slightly higher than that. Each division is giving us 500 millivolts, so you'll see that we've got slightly more than 3 volts peak to peak there. And you'll also notice that the symmetry of the steps isn't quite right. The bottom step is much greater than the other steps on the waveform, particularly the top step. So I'm going to adjust the trimmer here on the board now. That sets the output from the resistor divider network, and adjust that to give us exactly 3 volts peak to peak. And at the same time I'll be looking to make sure as I'm adjusting it I get some symmetry with the steps of the stair-step. So let me do that now. So I'm adjusting the preset, and if you look on the oscilloscope you'll see that the symmetry is improving. And if we now just check, just onto the vertical scale there, and check whether we've got, let me go down again, so we're looking for around 3 volts peak to peak, which is around, I think around there. So now you can see here we've got 3 volts peak to peak, and we've got reasonably good symmetry there of the steps of the waveform. And now I've moved the oscilloscope leads and I've connected it across the output here, so we've got the earth now connected onto that terminal of the output. And this time I'm going to adjust this preset here above the op amp to set the gain to give us exactly 5 volts peak to peak output. As you can see at the moment we've got much more than that coming out, so I need to adjust that trimmer there. So let me do that. So I'm adjusting the trimmer now, and you see the waveform is coming down. So we're looking for 5 volts peak to peak. Right, at the moment I've got the preset to the end of its travel at the moment, and I've got it only down to 6 volts peak to peak. So I think what I'm going to have to do is either reduce the value of the series resistor or temporarily short it out and just see if we can get the waveform down to 5 volts. Right, I've temporarily shorted out the 1K series resistor with the preset, and as you can see it's dropped down the amplitude, so let me just adjust this now to give me 5 volts peak to peak. Right, well there we have the adjustment now set, and we're getting now 5 volts peak to peak coming out the output, and I think you'll agree that the steps we have there are reasonably symmetry there at the moment. Now this actually proves a point, because what I've done on the board for the moment is I've just put standard value resistors in rather than the precise resistors I mentioned earlier on the circuit diagram, and even with standard value resistors here the output still looks pretty good. If you put the resistor values that I indicated on the circuit diagram, you'll find that the accuracy of the steps is much greater. But I think with standard value resistors that looks quite good. So what we'll do now is we'll have a look at the function of the selector switch there, and just see what effect it has on the waveform as I step through. Right, I'll just step through now with the selector switch. On the next step we just get one pulse coming out there, and if I go to the next one you can see now we've got 2 steps and then resetting, 3 steps and resetting, and 4 steps and resetting. So they're the other options we have. So we have 4, 3, 2, 1, and we go back to the stair-step waveform. Right, well I'll now move the shorting link there, the blue one, across so that it's giving us the 100 kilohertz going into the clock of the Johnson counter, and we'll just see the effect of that. Right, I've moved the link across and you can see immediately the frequency has increased, and let's have a look at the shape of the waveform, and I think it still looks quite good. We still have a reasonably good stair-step output there. Next thing we'll do, we'll just alter the yellow shorting link over, so we're using the adjustable oscillator, and we'll then adjust the trimmer there and just see the effects of having a variable oscillator feeding the clock input of the Johnson counter and the effect on the stair-step. Right, we now have the yellow link now connected on the 2 pins which connect the output from the adjustable oscillator to the clock input of the Johnson counter. You can see the waveform on the oscilloscope. The 3 pins above that at the moment is left open. That means that we have no connection for setting the divider of that IC, which means that the divider is operating at divide by 10. So if I alter the preset there at the moment, we should see the frequency of the stair-step waveform alter. You can see as I alter the resistance of the preset, we're altering the frequency now of the stair-step waveform. Now, as you can see at the moment, I'm doing that with a preset resistor on the board, but you could actually disconnect that and put some flying leads out to a variable potentiometer on the front panel and give you adjustment that way as well. Let me show you the effect now of putting the link in the connections below there that give us both divide by 1 and divide by 100. So let's just put the link now, and that's giving us a divide by 1 frequency out from the variable oscillator. We alter the, and again if I were to adjust the preset, we can vary that that frequency. Well, I hope you found this little project on the stair-step generator of some interest. I will make the schematic, the PCB artwork and the parts list available with a downlink below if you fancy having a go at this project. I'm sure there's lots of parts that we've included on this project today that we could include for future projects, such as the variable oscillator that we used. But in the meantime, I'm going to leave it there. If you found this of interest, please give me a thumbs up and subscribe, and hopefully we'll see you all again soon with another project next time. Bye for now.